Yeah, happy to. All right. So for the people I've not met before, hi, I'm Neil. I used to work at Anthropic doing mechanistic interpretability of transformers. I've spent the last couple of months as an independent researcher doing some work on grokking, and more recently getting extremely nerd-sniped by various kinds of field building and infrastructure creation for mechanistic interpretability. And in about a month, I'm going to be starting on the DeepMind mechanistic interpretability team. And this presentation is essentially an ad for a sequence of posts I've written called 200 Concrete Open Problems in Mechanistic Interpretability. The structure of this presentation is going to be a whirlwind tour through a bunch of different areas of mechanistic interpretability where there are things I'm confused about that I think I could be less confused about, and trying to give an example of work that I think is cool in that area, and recommendations for where people who are watching this who might want to contribute could get started. And I'll get more into resources at the end, but if you want to follow along at home, you can get to the slides with this link. You can see the actual sequence of posts with this link. And I wrote a post called Concrete Steps to Get Started in Mechanistic Interpretability that tries to give a concrete-ish guide for how to get up to speed here. And I recently discovered how I can use my website to create link redirects and use it everywhere. It's so satisfying. So to begin, I want to briefly try to outline what is mechanistic interpretability. So at a very high level, the goal of mechanistic interpretability is to reverse engineer neural networks. That is, take a trained network, which is capable of doing well on a task, and try to understand how it does well on that task. Trying to use whatever techniques work to try to reverse engineer what algorithm it has learned and what the underlying cognition of the agent is, or of the model is, not necessarily an agent. And one particular exciting reason that you might care about this is there are often multiple possible solutions that a model might learn to a problem, which look about the same, but might generalize wildly differently of distribution or break in different ways. And if we can actually understand what it's learned, we'd be able to distinguish between these. And the focus of this talk is not going to be on making a case for why I think you should care about mechanistic interpretability from an alignment perspective. My current favorite case for that is this post requesting proposals for interpretability work from Chris Olah, though generally I feel like someone should write up a good post on this because it's been a while. But my very brief justification is I think that a lot of alignment problems basically boil down to models could learn a solution that looks like being deceptive and evil, or learn a solution that looks like actually doing what we want. These are extremely hard to distinguish for capable systems, but if we could reverse engineer them, we might have a shot. And here's a cute, iconic picture from some work reverse engineering image classification models, where there's a small subset of the model where we can identify neurons that correspond to different bits of a car that then gets combined into a car detector that's like, if there are windows on top and wheels on the bottom and a car body on the bottom, it's probably a car. And a bit on the flavor of why you might want to do mechanistic interpretability is... So I think one thing that's just extremely hard about research in general, but especially alignment research, is just you really want feedback loops. You really want the ability to... you really want the ability to do things and get some feedback from reality on have you done something that was sensible or something that was incorrect. And while it is very easy to trick yourself in mechanistic interpretability, you are ultimately playing with real systems and writing code and running experiments, and the process of doing this gets you feedback from reality in a way that I find extremely satisfying, which I think also makes it easier to learn about. It is also, to my personal tastes, just extremely fun. So I have a pure maths background, and to me, the feeling of doing mechanistic interpretability is some mix between maths, because I'm reasoning about this clean mathematical object, computer science, where I'm thinking through algorithms, what the model might have learned, various ideas behind machine learning, and really engaging with the architecture of the underlying model, natural science, because I'm rapidly forming experiments, forming hypotheses, running experiments, trying to get data, and truth-seeking, because I have this ultimate grounded goal of forming true beliefs about the model. And to my personal tastes, this is just like way more fun than anything else I tried in alignments. And I seem a lot better at it. And I think that a thing you should do if you're trying to get into alignment is just try a bunch of things and see what things you find fun and which things you seem good at, and treat this as actually a fairly significant weight. And another feature / bit of advice is that if you want to learn about mechanistic interpretability, you should start coding extremely early and write a lot of code and write a lot of quick experimental code and get your hands dirty. It's both the bar for entry for actually writing code and running experiments, I think, is notably lower than some other fields. But I'm also just giving this as actual advice, since I often observe people who try to get into the field who think they need to spend weeks to months reading before they write any code, and I think this can kind of cripple your learning. And a final caveat to that impassioned sales pitch is I'm slightly confused because it seems like way more people are into doing mechanistic interpretability than they were a year ago. And it's like plausible that on the margin more people are interested in this than should be out of all people trying to get into alignments. I'm kind of confused about what to do about this, and I still want to give talks about why mechanistic interpretability is great, how you can get into it, and how you can contribute, but I feel like I should at least vaguely flag that if you're almost indifferent between another area of alignment and mechanistic interpretability, plausibly it is less neglected in other areas, though on the grand scale of things, everything in alignment is ridiculously neglected and this is terrible, and yeah. I'm confused about how to orient to that, but I figured I should at least raise the point. I should also say that in terms of philosophy of questions for this talk, the structure is intended to be a rapid whirlwind tour where ideally you don't need to understand any section to understand the next one, and thus I'd ideally leave questions to the end unless you think it's important for the flow of the talk within that structure. So the kind of mechanistic interpretability I care the most about is transformer circuits, the study of reverse engineering language models, which in this case are all implemented as transformers, a particular neural network architecture. I care a lot about this because I think that by far the most likely way to get AGI, especially if it happens in the next 5 to 15 years, is by something that looks a lot like large language models trained on something that looks a lot like transformers. And it is wildly out of scope for this talk to actually explain what transformers are, but I'm going to do my best shot at giving a sub 5-minute whirlwind talk. So, at a very high level, the way that a transformer like GPT-3 works is its input is a sequence of words. Technically, it's a sequence of tokens, which are like subwords, but you don't need to care about this. The output of the model is a probability distribution over possible next words. That is, we're just feeding a bunch of text into the model and training it to predict what comes next in that text. A weird feature of the model is that its output actually has a probability distribution over the next token for each token of the input sequence. Because the way the model is set up, the kth output can only see the first k inputs, so it can't just cheat. The key thing here is just the model outputs probability distributions over next words. The model's internals are represented by this thing called the residual stream, which importantly is a sequence of representations. That is, after each layer, there is, for every word in the input sequence, there is a separate value, internal value in the network. That is a separate internal copy of the residual stream for that position of the sequence. And this is this kind of 2D thing where you have one for each input word and one for each layer. And unlike in classic neural networks, each layer is an incremental update to this residual stream. The residual stream is a running total of all layer outputs, and each layer is just taking in information from it and changing what's in it a bit, rather than in a classic neural network where each layer's output is just all that the model has at that point. And intuitively, the way I think about an intuition that I think is useful to have when you're first learning about transformers, but is not actually perfectly correct, is that you can think about the residual stream for some word as being the model's internal representation of that word plus a bunch of context from the surrounding words, and that as the layers go on, the representation of the residual stream gets more and more sophisticated context included. And there are two types of layers in the model, each of which updates the residual stream. The first is attention layers. These move information between words, and they're made up of heads. Each layer is made up of several heads, each of which can act independently and in parallel, and each one is choosing its own idea of what information should be moved. And a lot of the interpretability progress has been trying to interpret heads. And trying to interpret heads generally looks like trying to understand in what ways the model would want to move information around and how it moves information around. And the second type of layer are the MLP layers, which stands for multi-layered perceptron. And these do not move information between words. They act in parallel on the model's internals at each sequence position, and they process the information that the attention layers have moved to that word. And combined, the model consists of an attention layer, an MLP layer, etc., stacked up a bunch, and each of these incrementally pulls in more and more context for each word until at the end of the model, it's able to convert that to a best guess what the next word will be. Thus ends my whirlwind tour. I have a what is a transformer tutorial and a how to implement GPT-2 from scratch tutorial that you should totally go check out. And the internet is also full of other people's attempts to make transformer tutorials if you want to learn this. Generally, this is just a thing you really want to learn if you want to do good mech interp work. Though a bunch of the problems I'm going to talk about, you don't actually need a deep understanding of transformers to get traction on. But I hope that whirlwind tour is interesting to people. I'm now going to move on to actually digging into areas of concrete open problems. So the first problem area is analyzing toy language models. So by a toy language model, what I mean is I try to train a language model analogous to a cutting-edge thing like GPT-3 or ChatGPT. You keep the training setup of train on a load of text and try to predict the next word the same. And you keep all of the architecture and details the same. But rather than having like 96 layers like GPT-3 has, you just have one layer or 2 or 3 layers. And sometimes you might want to remove some of the additional complexity in the model, like having an attention-only model, where you just remove the MLP layers and thus only study its ability to move information around. And I think that toy language models are a pretty exciting thing to study because A, they are just dramatically easier and more tractable to study and try to really get traction on reverse engineering. But they're also complex and hard enough that I think we can learn real things from them, and that there's at least decent suggestive evidence that the things we can learn do generalize to real models. A good case study of this is induction heads. So induction heads are this circuit we found in this paper I was involved in called A Mathematical Framework for Transformer Circuits, where we studied toy attention-only language models, and we found that a thing that often came up in language was some text that was repeated in a sequence multiple times. Like, there was a forum comment that someone quoted further down, or a news article headline that was then repeated in the text, or whatever. And the model learned this fairly simple, yet still somewhat sophisticated circuit where two heads work together to say, has the current token appeared in the past? If yes, look at the thing that came after that and assume it will come next. And we called these induction heads. Naively, this might not actually sound that exciting, but these turned out to be a really big deal. Such a big deal that we had an entire follow-up paper on them. Two notable things about them is that they appear in basically all models we studied. There's a fairly narrow band in training when they appear, and basically all of the induction heads appear. Here's a pretty sharp, the yellow bar is the region where you go from no induction heads to having induction heads. And most excitingly, they seem really important for this weird capability that language models have called in-context learning, where the model is capable of using words far back in its context to predict what comes next. This is analogous to, say, reading a book and remembering some detail that came up 5 pages ago in order to predict what's going to happen next. This is kind of surprising that a neural network can do this. And it turns out that induction heads are just a really crucial part of how the model is able to track these long-range dependencies. And the narrow band of training, when they appear, exactly coincides with the narrow band of training where the model suddenly gets really good at this. And a further exciting thing about induction heads is that we've made some decent traction in actually reverse engineering what's happening in them. I am not going to try to explain this diagram, but this is copied from a great blog post from Callum McDougall that is linked in the slides that you can go poke around in and try to read about how these actually work. I will flag we do not actually have a complete understanding of induction heads, and there are additional subtleties and complexities that we're still kind of confused about. But the overall message I want you to take away from the section is just that there are things that we are actually fairly confused about in toy language models, yet they are also sufficiently simple that we can get some real traction on this. And the insights we learn genuinely seem to transfer to real models, or at least give us some useful insights on them. And a particular concrete problem that I would really love someone listening to go and try to take on is one of the big open problems, in my opinion, in mechanistic interpretability of transformers is how to understand the MLP layers of a transformer, how to understand the bits that are about processing the information in place rather than moving it between positions. And I think a particularly promising way to get started on this would be to just take a one-layer transformer with MLPs and try to understand just a single neuron of that. I assert there is just not an example of a single neuron in a language model that we can claim to really understand. And this seems kind of embarrassing. And in the post accompanying this section, I open source some toy language models I train that you can just go and play around. The next area of concrete open problems is what I call looking for circuits in the wild, where that is looking at real language models that weren't just trained in kind of like tiny toy settings, and taking something these models are capable of doing and trying to reverse engineer some circuit behind. The work that most motivates this section is this great paper called Interpretability in the Wild from Redwood Research, which studied how GPT-2 Small can do this particular grammatical task of indirect object identification. That is, seeing a sentence like, when John and Mary went to the store, John gave the bag to, and realizing that the sentence should be completed with the word Mary. And this is simultaneously a somewhat complicated task where it's like not totally obvious to me how a model could solve it, but also not an incredibly hard or sophisticated or complicated task. And interestingly, it's also fundamentally a task about successfully moving information throughout the context, because you need to figure out that John is duplicated, you need to route the words that are not duplicated to the final token. And in their paper, they did this heroic effort of reverse engineering that found this, I believe, 25-head circuit behind how the model does this, that roughly breaks down into using some heads to figure out that John is repeated, moving these to the final token with some extra heads, because, again, the model has a separate internal representation at each word in the input sequence, and then having a cluster of things that moves all names that are not repeated and predicts that those are complex. And I would just be really excited to see people trying to find more circuits in real models. And excitingly, every time there's a area I'm pointing to where I'm like, and here's some existing work that you could be inspired by, it saves a dramatic amount of effort if there's some existing work that you can crib from and use as starting points. And I made this demo notebook called Exploratory Analysis Demo that demonstrates what I consider to be some fairly straightforward yet powerful techniques to get traction on what's going on inside a model, and use them to speed run half rederiving the indirect object identification circuit. And a concrete question that I think you could get some good traction on answering with a combination of my notebook and the underlying transformer lens library that I wrote that it uses to play around with models, and the code base Redwood put out with their paper, is what does the indirect object identification circuit look like in other models? The library included lets you load in another model by just changing some text at the top. Is it the case that the same circuit arises? Is it the case that the same techniques work? Is it the case that actually we need to basically start from scratch and there's like a new, deep, laborious effort every time there's a new circuit? Who knows? I think this is something that you could get traction on, and is a question that I'm pretty interested in. And let's get back to this. So, new area of concrete open problems, training dynamics. So, it is just a fact about the universe that frequently when we take a neural network and we give it a bunch of data or some task to learn, and then we apply stochastic or gradient descent to it a bunch, it ends up with a solution to the task that is reasonably good. I'm extremely confused about why this happens. And I'm also very confused about how this happens. What are the underlying dynamics? How does the model navigate through the space of all possible solutions it could find? Is it the case that there's just some clear canonical solution that it's always going to end up in, even if its path there is somewhat different? Is there a lot of randomness where it could just end up at solution 1 or solution 2 kind of arbitrarily? Is it the case that we can influence these training dynamics, or is it just really overdetermined and it would break anything we try doing? And I think that a particularly promising way to get traction on a lot of these questions is to train models that can demonstrate some of these problems in a smaller, more tractable setting, and then trying to reverse engineer these. And an example of some work that I did here. So there was this wild paper from OpenAI at the start of last year on this phenomena of grokking. So grokking is this thing where if you train a small transformer on some specific algorithmic tasks, in this case modular division, and you give it, say, a half of the data as training data, if you train it on that task, it will initially just memorize the data it sees and do terribly in the data it doesn't see. But then if you keep training for a really, really long time, in this case, about 100 times longer than it took to memorize, it will sometimes just abruptly generalize. And to underline, it suddenly generalizes despite never seeing, despite just looking at the same data again and again, and never actually having a chance to look at the unseen data. And this is a kind of wild mystery that a lot of people in the ML community were interested in. And this work I did on it, I trained a even smaller model to do modular addition and stared really hard at its weights and found that it was doing this wild trig-based algorithm where it learned to think about modular addition as rotation around the unit circle. It learned a lookup table that converted the inputs to inputs A and B to rotations by angle A times constant and B times constant around the circle. It learns to compose those to get the rotation A plus B, and then to get out the correct answer C, it learns to apply the reverse rotation C, and then look for which C got it back where it started. And because it's around a circle, it automatically gets mod n. And you really don't need to understand the specific details of this algorithm, but it is just incredibly wild, in my opinion, that this is just actually a thing that the model learned. And if we look at the model during training, we can see, using our understanding of the circuit, we can see that even during this plateau, the model, even during the period before it actually generalizes, the model has shown significant internal structure to its weights and representations, and can basically just use our understanding to look inside the model and see what's going on during training. And a concrete problem here that I'd be excited to see someone poke around at is, in my grokking work, we dove really hard into reverse engineering this modular addition, but I also exhibited grokking in a few other contexts, like 5-digit addition, or a model trains to have induction heads on a small algorithmic task, and these also seem to grok. And I would love for someone to take, say, the induction heads task, try to really dig into what's going on there, and see if you can use this to understand why that one groks, and see how much these insights compare. Alright. New area of open problems. If you didn't follow the previous ones, you can just start paying attention again here. Studying neurons. So, our best understanding of how complicated neural networks work is that a lot of what they're doing is they're learning how to compute features. Where by feature, what I mean is some function or property of the input. For example, this token is the final token in Eiffel Tower. This bit of the image contains a dog ear. This image is about Christmas. This number describes a group of people. And this is our best guess for how models work. And I would really like to get a much better understanding of what kinds of features actually get learned in language models, and where do these get learned? Because what seems to happen in, say, image models, which we've got a much better handle on, is that those models seem to develop specific families of simple features that get combined to more and more complex features until eventually you get really sophisticated and high-level ones. Here are some great neurons from this paper called Multimodal Neurons, which studied neurons in a model called CLIP, which contains both image and text parts. And they found all of these wild high-level neurons, like a Donald Trump neuron, or a Catholicism neuron, or an anime neuron, or a teenage neuron. And it's like, what? And we are much less good at reliably figuring out what neurons correspond to in language models. But the scope I'm aiming for in this area is more just try to look at what neurons represent and use this to get a better handle on what kind of things the model is actually learning, even if this is neither complete nor, even if this is not complete nor fully rigorous. I think we would just still learn a lot. And a pretty janky but effective technique here is this idea of looking at max activating dataset examples. That is, you pick a neuron, you feed a bunch of data through the model, and you look at which text most activated that neuron. And if the top 20 bits of text a bunch of them seem to have some consistent pattern, that's reasonably good evidence that the model has actually learned that pattern as a feature. And there's this great paper called softmax linear units from Anthropic that I was vaguely involved in, where this isn't actually a focus of the paper. One of the things they do is just explore what kind of things are learned by neurons. And we have things like this base64 neuron, which observes that often you get strings that are written in base64. And that if this happens, there's a bunch of specific tokens that are more likely to occur than otherwise, and a bunch of common words that are really unlikely to occur. There's disambiguation neurons. So this is a family of neurons which look at the token D and observe that D comes up in a bunch of different languages and contexts. And it's the same kind of text in each of those, but in Afrikaans or English or German or Dutch, you want to think of it as a completely different thing, and the model seems to learn separate features for D in Dutch, D in German, etc. There's also more abstract and sophisticated neurons. Here's a neuron which, in the middle layers of a much larger model, which looks for numbers that implicitly describe groups of people. And one particular notable thing is that the way language models work is they can only use text that came before rather than afterwards. So it knew that, say, 150 or 70 was going to describe guests, despite this not occurring before. And I made this somewhat janky and under construction tool called Neuroscope, which just collects and displays the max activating dataset examples for a bunch of neurons, all neurons in a bunch of language models. And I think an extremely low barrier of entry project would just be go poke around in there and see what you can find. I'm particularly interested in seeing what kind of interesting abstract concepts do models seem to learn around the middle layers of larger models. And I'd be particularly excited for you to then go and try to validate this understanding, either by actually reverse engineering something in a smaller model, or just by feeding in a bunch of text that you've generated yourself to the model, and seeing what hypotheses you can confirm or falsify about what text should activate that. And just seeing how reliable pattern spotting in text that activates a model actually is. Again, if you go to neelnanda.io/cop-slides, you can find these slides and all of the many links in there. All right, next category of problem, polysemanticity and superposition. So one thing that I somewhat glossed over in the previous category is this core problem in interpreting neurons, which is the idea of polysemanticity. So it seems to be the case that while in image models, neurons often seem to represent single concepts, sometimes they didn't. So here is one of the neurons studied in the multimodal neurons paper. And this is a technique called feature visualization that roughly gives you this funky psychedelic image that roughly models what that neuron is most looking for. And we see this kind of playing card dice style thing. We might think it's a kind of game neuron. But it turns out that if you look at the inputs that most activate it, half of them are about games or cards or stuff like that, and then half of them are about poetry for some reason. And it's possible that there's just some galaxy brain thing here where poetry and dice and cards are all collectively some coherent feature that's useful for modeling the task that I'm totally missing. But this seems to happen all of the time in language models and is incredibly annoying. And generally it just seems likely to be the case that models have just decided to represent multiple things in the same neuron, or at least kind of representing things spread across many neurons. And our best guess for what's going on here is this phenomena called superposition. The idea of superposition is that a model tries to represent more features than it has dimensions by squashing those features into a lower dimensional space. And this is kind of analogous to the model simulating a much larger model with many more parameters and features, which is obviously useful because bigger models can represent more things. And that the model has decided that simulating a larger model with a bunch of interference and noise is good and worthwhile and a sensible trade-off. And if you have more features than you have neurons, you obviously can't have a feature per neuron, and you're going to have to be compressing and squashing them in some complicated way. And Anthropic had this awesome paper called Toy Models of Superposition, which looked at, can we build even a toy model that just actually provably learns to use superposition? And is it the case that is it ever the case that superposition is actually useful? To which the answer is yes, it is. It's very annoying. And so what they did is they just built this really, really simple setup where you have a bunch of features that are input to the model. They need to be squashed down into some low-dimensional space. And here you have 5 input features, and they need to be squashed into a 2-dimensional space. And then we measure how well the model can recover these. And it turns out that if the features are there all the time, such that they interfere with each other a lot, the model just learns a feature per dimension. If they aren't there as often, sparsity means 80% of the time a feature is just set to 0, the model decides to squash 2 per dimension. And if they're even less frequent, the model decides to squash 5 into the 2 dimensions in this pretty pentagonal configuration. And if you dig more, you find that this thing wasn't just a spontaneous thing that occurred because we had just 2 hidden dimensions. it turns out if you make the model squash things into more hidden dimensions, they spontaneously self-organize into clusters of features that are each in their own orthogonal subspace. And that if you plot things, they can form energy levels according to what configuration they're in. Like some models have tetrahedra, where 4 features fit into 3 dimensions. Some models have a mix of triangles with 3 and 2, and antipodal pairs with 2 and 1. And I'm not really going to try to explain this diagram properly. You should totally just go check out the paper if you're curious. But some open questions here that I'm pretty excited about people exploring. The first is just, this paper makes a bunch of predictions about what superposition might actually look like in models, when it might occur, what it might look like. Can you just go and poke around in a model and get any traction on figuring out whether any of these occur? In particular, if you start with one of the circuits we've already got a lot of traction on, like induction heads or indirect object identification, I think you might actually be able to get some interesting data here. And the second category of problem is, I think there's lots of things I'm confused about to do with how models could do computation in superposition, and how models can kind of squash more features than they have neurons, and then apply some nonlinear function to process information, and they get something useful out. But it seems like they can do this. And the paper very briefly explored this, but in the relevant concrete open problems post, I try to spell out a bunch of other angles I might take and things I'm still confused about. And yeah, I generally think that dealing with superposition is probably the biggest open problem in mechanistic interpretability right now. And I am very excited to see if we can get more progress here. Alright, new category of problems. If you zoned out, you can start paying attention again. Techniques and automation. So, fundamentally, the thing we are trying to do when reverse engineering models is to form true beliefs about model internals. Forming true beliefs is hard. And one of the main things that lets us get anywhere on this is having good techniques, having well understood, principled approaches that we can apply that will actually help us gain some traction and gain some insight into what's going on inside. And I think that there's lots of room for progress here. Building new tools, building a better and more reliable toolkit, building a better understanding of our existing toolkit. One concrete example of this is, so a technique that's pretty popular in some circles of interpretability is ablations. That is, you pick some bit of a model and you set this bit of the model to 0, and you check, okay, I've set this bit of the model to 0, how does its performance on a given task change? If you set a bit to 0 and the performance tanks, then probably that bit mattered. If you set it to 0 and performance doesn't tank, then probably that bit didn't matter. Is a naive thing, but it's very reasonable to think. That's something that I thought. But one weird-ass outcome of the interpretability in the wild work was they found these things called backup heads, where it turns out that when you delete certain important heads, other heads in the next layer or two change their behavior to near perfectly compensate. And it's like, what? So what this graph shows is that if you look at the direct longitude attribution of a head, that is the effect of that head on the output of the model, what you observe is that when you delete this particular important head, so the original effect is like 3, after you delete it, it's 0 because it's deleted. 2 other heads, which are really important, just kind of stop matter, to significantly change their behavior, and go from really big effects to fairly small negative effects, and fairly small visual effect to pretty big next effect. And it's like, what? Why does this happen? I would not have expected this to happen. I'm extremely confused. I would really like to get a much better understanding of what is going on here and what kind of pathological cases might exist for other techniques I think are cool. And one concrete open problem here is just, how general is this backup head phenomenon? Can you find backup previous token heads which attend to the previous token only if an earlier previous token head is deleted? Can you find backup induction heads or backup duplicate token heads? I have no idea. I would love someone to just go and look. Or are backup heads purely results of training models with dropouts? Technique where you just randomly set some bits to 0 during training and try to make it robust to that? I have no idea. And the exploratory analysis demo that I made includes a bit at the end where I replicate the backup name of a head results to hopefully save you some effort. I'm generally trying to emphasize demos and tooling because if you're just getting started in a field and you want to try making traction, it's just really helpful to have something you can crib off of and copy from rather than even start from scratch. Also, if the thing does not succeed at being useful and you still need to write a load of things from scratch, please let me know. I will attempt to fix it. A different kind of thing that I fit into this broad category of techniques and automation is automation. One of the most common, and in my opinion, fairly legitimate critiques of mechanistic interpretability is that a lot of the successes people have had are very labor-intensive. And maybe they worked on small models, and maybe they'd work in principle on large models, but where it would just take like years to really get traction on actually fully understanding a incredibly large and complicated model. And where the bigger models get, the more and more intractable it will seem. And I'm pretty excited to see effort trying to take the techniques and know-how and insights that we have and trying to think through how you could actually scale these and automate these. One very simple, dumb example I made is this thing that I call an induction mosaic, where, so a nice property of induction heads is that they work even on sequences of purely random tokens if the sequence is repeated. And if, it works on the sequence, even if it works on a sequence of random tokens, you got the random tokens and you just repeat it, and it always attends to the token immediately after the first copy of the current token. And this is an incredibly easy thing to code and then just check for. And this is a heat map where the y-axis is which head, the x-axis is which layer, and the color is how induction is that head. And we can see that across 41 models, there are induction heads in all of them. And we can even observe some high-level patterns, like most models only have induction heads in the second half. Apart from GPT-J, for some reason. Why does this happen? I have no idea. And I made this mosaic using my transformer lens library, which has the fun feature that you can change which model you have loaded by just changing the name of the model in the input. And I would really love for someone to go and just do this for all of the kinds of heads that we understand, e.g. all the heads in the indirect object identification circuit, other simple kinds like duplicate token and previous token heads, and then just make a wiki where for every head in all open source language models, we just have a brief summary of what we know about it. I think this would be a really cool thing to exist that just wouldn't be that hard to make. And more generally, I think there's a large amount of scope to take the stuff that we already know and are already good at, and to think about how you can distill it to techniques or how you can distill it to things that are more scalable and automatable. Though I do personally,
Sorry, sorry to interrupt. There was a question that was asked a little bit ago. We're a few steps removed here. Lisa is wondering, a paper you mentioned a little bit ago, if it could be interpreted as model redundancy. She says, did this paper also look into what makes a head count as an important head worth creating a backup for? I don't know if that's still applicable or not, but
the answer is no, they had not looked into this, but you could look into this. And yep, who knows? I'd love to see the answer to that. This is just another data point in the general vibe I want to convey. If there's just so many concrete open problems here that I don't know the answer to, and I'd love to know the answer to. All right. Final area of concrete open problems. Actually, no, they're supposed to end at past or the hour. I normally assume talks are an hour long by the calendar event till the hour. Well, no one else is me, I'll just assume that it's till the hour. Alright, so, but I'm going to wrap up soon anyway. Alright, so...
You're welcome to go longer. We have like a Slido for Q&A questions as well. I'll post in the Slack after you're done. But yeah, the timing is up to you.
Yeah, if you could post a Slido in the Slack and Zoom chat now so people can like start putting in questions, that'd be great. Unless you've already done that. Alright, so final area of concrete open problems I want to poke at is interpreting algorithmic models. That is, train a model on some synthetic algorithmic task and then go and try to reverse engineer what happened. What algorithm did the model learn? And I think obviously, this is even more removed from actually being able to reverse engineer cutting-edge models than the toy language models that I was talking about earlier. So you kind of want to check that what you're doing is actually remotely useful. One angle is that if we can, it's a lot easier to really understand what's going on in an algorithmic model where there's a genuine ground truth. And this can serve as a test bed for us to explore and understand our interpretability techniques. It can also be useful to build toy models to simulate things that we believe large models to be doing, so we can try to understand them. For example, it's plausible to me that a useful way to have gotten traction on the interpretability of the wild work might have been to train a toy model to do a synthetic version of that task, seeing how small you can get it, and seeing what that model did. And I think things like McRocking work and the toy models of superposition are further things in this vein. But all of that is kind of rationalization. The actual reason that I'm recommending this is I think it's just a really easy place to get started that will help you build real intuitions and skills. And that just pick a model on any algorithmic task and then try to get traction on it is just a pretty great first project, even if it isn't actually remotely useful. And a demo / tutorial that I made is so I was curious, if you don't explicitly tell a model anything about which position things in the sequence are, can it rederive these? For sophisticated reasons, the way transformers work is that they kind of treat each pair of positions equivalently, unless you explicitly hack them to care about positional information. And it turns out that if you don't tell it anything about position, but you only let it look backwards, a two-layer model can just learn to rederive its own positional embeddings if trained on a really simple dumb task. And I released a Colab notebook along with this, with the relevant codes, but I also decided to record myself just trying to do research on this for like 2 hours. And hopefully this is a good model to try to build off of if you want to go and try to interpret an algorithmic task. Alright, so thus ends the whirlwind tour of areas of open problems. Some concrete resources to learn more. My 200 concurrent problems in mechanistic interpretability sequence, though I really have not been counting, and I tend to add more than I delete when I edit, so it could be like 300 at this point. If anyone wants to count, let me know, be my guest. A guide on how to get started in mechanistic interpretability. I generally recommend starting with this one unless you just feel really psyched about jumping straight into an actual open problem. I try to give concrete steps with success criteria and goals, and to generally guide you through the common mistakes I see people make, like read for weeks to months before they write any code, or be really intimidated by specific things that aren't actually that hard. I wrote a comprehensive mechanistic interpretability explainer, which is basically an enormous brain dump of ideas and concepts and terms and jargon that I think you should know if you're trying to learn about mechanistic interpretability, with extremely long tangents, examples, motivations, and intuitions. I think it's both a pretty productive thing to just read through to get a sense of the fields, if you're in the mood for a long haul, or as a thing to just search whenever you come across an unfamiliar term. And finally, my transformer lens library, which attempts to make it so that if you are trying to do some research on a question that involves reverse engineering, a model like GPT-2, I try to make it so that the gap between have an experiment idea and get the results is as low as possible by trying to design an interface that does all of the things I care about doing as a researcher as fast as possible. And anecdotally, other people seem to also find this useful, though who knows. But doing mechanistic interpretability with no infrastructure is a pain. So hopefully this is helpful. And yeah, zooming out of it, I kind of just want to give the high-level framing that the spirit I want to convey in this talk is mechanistic interpretability is a interesting, alive field that just has lots of areas where people could add value, and lots of things we don't know that I would really like to understand better. And the bar to entry for engaging with these and making progress on them is not that high. I also want to make sure I also convey that doing research is just actually fairly hard, and you should go into your first research project expecting that you're going to get a lot of things wrong, you're going to make a lot of mistakes. Ultimately, the thing you produce probably won't be like groundbreaking research, and it might have some significant flaws, especially if you don't have mentorship. But also that the best way to learn to get to a point where you can do useful work is just by trying, and by getting your hands dirty, getting contact with reality, and actually playing around with real systems, and having some clear focus and prioritization of this is an open problem that I want to understand. Let me direct my learning and coding and exploration so that I can try to get traction on this, is, in my opinion, just one of the best ways you can learn how to get better at doing real mechanistic interpretability research. And I think we'll have at least some transfer to just doing real research in general. And yeah, I try to link to a bunch of resources. I will also just emphasize again that it is plausible to me that too many people are trying to do mechanistic interpretability. And if you feel equivalently drawn to other things, you should totally go explore those. But if you're going to try to explore mechanistic interpretability, please try to do it right. And I hope these various resources and framings are helpful to that. All right, I am going to end the main presentation here, but I'm very happy to take a bunch of questions for a while. Question 1. Do I think interpretability research into model-based RL will be useful? Any cool previous papers in this area? So my answer to most questions about do I think interpretability research into area X would be useful is yes, because I think that the amount we understand about networks is just pathetically small. and that if we could understand more, this would be great. And yeah, this seems like a thing that I would really love to have more insight into. If I'm engaging with the question more from the spirit of prioritization, would I rather have interpretability research into model-based RL rather than other areas? Model-based RL is jargon. For people who aren't familiar, RL is reinforcement learning, which is the study of if you train a model to be an agent that is taking an action in some environments, and you give it some reward saying you have done good things or you have not done good things, how can it learn strategies to get good rewards? And I believe that model-based specifically, though I'm not an RL person, so this could be wrong, is when the model, when part of the model is explicitly designed to simulate the environment it's in, and using that in order to form better plans and strategies to get more reward. And yeah, so fundamentally, I think that there are two ways I would think about reinforcement learning interpretability being useful. The first would just be, I do not think we understand reinforcement learning at all. I would really like to be way less confused about this. And I think that just aggressively optimizing for whatever seems most tractable, just to learn anything at all, seems great. And this can look like simple tasks, this can look like smaller models, this could possibly having an explicit model-based thing will be even easier. And then the second angle of why I care about interpreting RL is because lots of questions and concerns to do with alignment fundamentally revolve around things to do with how models do things. And yeah, fundamentally around how do models do things? And what does it even mean for a model to be an agent or pursue goals? Do models have internal representations of goals at all? Are models capable of planning? Who knows? And I don't have strong takes whether model-based or model-free RL is the best way to approach that. And finally, the actual thing that I care about with all interpretability research is, will this actually be useful for whatever AGI looks like? And the popular way of using RL on cutting-edge models today is reinforcement learning from human feedback, which uses an algorithm called proximal policy optimization, or PPO. And to my knowledge, PPO is not model-based, which makes me less excited about model-based focus. And I'm not aware of any cool previous papers. I do, actually, 2 days ago, yesterday, I made a post in the sequence on reinforcement learning that tried to give some takes on how I think about reinforcement learning in general, how I think about interpreting reinforcement learning in general, which is hopefully useful to check out. Next question. Is there any research or recommendations you have to look into automating circuit discovery in large language models? So let's see. There's two things that I think are particular. So one thing which I'm pretty excited about here is Redwood Research have this sequence on this algorithm called causal scrubbing, which is their attempt to make something that is actually automatable. That is their attempt to make an approach to verifying that something is actually a circuit that can just be automated and is also highly rigorous. I'm very excited about causal scrubbing, building infrastructure of causal scrubbing, scaling it up, checking how well it works. They're currently running their large-scale remix research sprint style program, which is probably going to get a bunch of data on that. But I definitely check out causal scrubbing. And I would also, Arthur Conley, who is a researcher at Redwood, recently had this post on automatic circuit discovery, where he was trying to write some code he was an author on the interpretability of the wild paper and was writing some code to try to automate how to discover that circuit. I haven't engaged with this that closely, but I think it's pretty cool. More generally, so my high-level philosophy of automating interpretability is, I think that a thing that I frequently see in people getting into the field, which in my opinion is something of a mistake, is that people see mechanistic interpretability and they're like, this is cool, but it's so labor intensive. I'm not interested in doing a project that involves labor intensive approaches to discover circuits. And I want to fully jump to automation or incredibly scalable things. And I think there is a valid spirit to this. I do think that having things that are automated or scalable is extremely important. But I also think that we are significantly more constrained by actual true knowledge about networks and network internals than we are constrained by ideas for techniques that might scale and might automatically find things. And in my opinion, the right way to do work on discovering automated ways to do mech-interp is by starting with examples that we understand like pretty well, trying to distill this and find techniques that could uncover this faster, i.e., are there ways you could automatically discover the interpretability in the wild circuit, and then trying to scale up these techniques by finding novel circuits, and in the process of doing so, use this to validate how well your technique actually works with a bunch of more ad hoc and labor-intensive approaches on the side. Well, is non-mechanistic interpretability a thing? Yes, I think it would be fairly rude of me if someone left this talk thinking that the early interpretability that existed is mechanistic interpretability. Interpretability is a large and thriving field of academia that I do not feel qualified to give clear summaries of. Generally, there are just lots and lots of things that people do. Some high-level categorizations would be things like there's black box interpretability techniques, which just look at the model's input and output, and maybe differentiate through the model and try to generate explanations for why it produces this output. Things like saliency maps are things that try to figure out which parts of the inputs affect an output. There's the entire field of explainable AI, which often judges their metric of success as how we produce an explanation that is useful to users. I don't feel that excited about these areas, especially from a alignment perspective. There's also a lot of areas of academic interpretability that is trying to really engage with models and model internals. There's this good survey paper called Towards Transparent AI that I just copied into the Zoom chat. If someone could collect these links and like put them in Slack or something afterwards, that would be useful. Yeah. Do I have other things to say on this? Yeah, I mean, mechanistic is kind of a fuzzy word. There's mechanistic as a de facto description of the community of people who work on what I call mechanistic interpretability, which tends to be people in the alignment community, and it tends to be people at industry labs or non-profits like Redwood. And there's in contrast to the things that actual academics at academic labs or people in more mainstream bits of our research do. And then there's the actual research philosophy of what it even means for something to be mechanistic or not. And it's very easy to get into stuff that splits hairs. I also recently got into a bunch of arguments on Twitter with people in more conventional academic interpretability about what even the differences of mechanistic stuff were. And you should go check out my Twitter replies if you want a lot of in-the-weeds discussion. All right. What do I think about trying to interpret reward models? that seems great. I really want to see compelling results trying to interpret reward models. I was not actually aware there were papers doing that, which either suggests those papers aren't very good, or just that my ability to hear about papers is kind of bad. So if anyone's interested in, if whoever read that's interested in emailing me those papers, I'd appreciate that. Generally, I'm just very excited about trying to interpret reward models. For context, the prevailing way that language models are trained with reinforcement learning is this technique called RL from human feedback, where the human operator gives them some feedback and they're trained to optimize it. And reward models are a subpart of that approach, where they're a subpart of that approach where what happens is that the language model has a separate thing called a reward model. I say separate as often just an extra head on the model outputs, and this predicts what feedback a human would give, and that the human feedback is used to make sure the reward model is in sync, and the model actually learns from the reward model, which is very janky, but is the main way that using human feedback is remotely economical, because humans are expensive in a way that GPUs are not. Also, humans are slow in a way that GPUs are not. Yeah. Interpreting reward models is great, probably pretty hard. I would definitely start with some kind of toy model in a simpler setting. Though a nice thing about the reward models of language models is they're basically exactly the same network, but with a different unembedding matrix at the end. And so hopefully a lot of the interpretability work will transfer. One fairly ambitious project that I'm keen to see someone do is to take a tiny model, like a 1-layer language model or a 4-layer language model, and try to simulate RL from human feedback using, I don't know, a larger model to just automate what that feedback should be. You probably don't even need GPT-3. I'm sure GPT-2 could do that. And I've totally not worked out in my head what the right task here is, etc. But I expect I'd be excited to see what comes out of this. Cool. Next question. Okay. Do you expect larger models to outgrow the need to create polysemantic neurons? My guess is that... Also, I observe that the question below that says, what makes interpretability research less promising for alignment? I don't really understand what this means, and it'd be useful if you could put a clarification in the Zoom chat. In particular, what I said previously was that I think black box explanation-based interpretability research is less promising for alignment, rather than interpretability research in general. But you might want to put a clarification before I get to it. Alright, case question. Do you expect larger models to outgrow the need to create polysemantic neurons? So I think there's two questions here that I want to disentangle. The first question is, should a more capable model that also has a bunch more neurons no longer need polysemantic neurons? And I'm like, no. Seems extremely unlikely. There's this useful intuition they explore in the toy models paper called the feature importance curve, where you can imagine just having a graph where the x-axis is just the set of all possible features that it could ever be useful to model about an input, from things like this text is in English versus French, to, I don't know, the content of Neel Nanda's SERI maths talk. And, yeah. So, this basically seemed like it should be not quite infinite, but incredibly long-tailed. And the features that are further and further out are less and less useful, and less frequent, but still better than nothing. And so we should expect that if models can, they're going to want to represent as many of these as they can. And this seems like a thing that's still going to result in polysemanticity. If you mean holding capabilities fixed, but giving them way more parameters, can they outgrow the need for polysemantic neurons? I don't really know. This is also just pretty hard to do, because if you give something more neurons, you're inherently giving it more parameters. But a thing that I'm kind of curious about is what happens if, rather than having 4 neurons per residual stream dimension, the model has like 100. Entertainingly, if you look at the 11 billion parameter model T5, for some unknown reason, they trained it with 65 neurons per residual stream dimension. I have no idea why. Actually, 64. I have no idea why, but it might be an interesting thing to study to see if things are less polysemantic there. Though T5 is an encoder-decoder model, which are a massive pain for other reasons. Alright, next question. Can we rule out that the neurons that seem weird, e.g. poetry games, are just being looked at in the wrong basis of the layer activation space? So, I do not think that we currently have enough evidence to confidently rule that out, though I don't think it would be incredibly hard to at least collect some evidence for that in a one-layer language model. A concrete open problem someone watching this might be able to contribute to. So the two things you want to disentangle here are, is it the case that the model has as many features as dimensions, but rather than having a feature direction correspond to a neuron, it corresponds to some weird things spread across a bunch of neurons? And I don't know. And then on the flip side, there's the question of, are there more features than dimensions, such that even though the model really wants to align them with neurons, it just can't, because there's more features than neurons. And my guess is that if there isn't superposition, the model is just going to really want to... Yeah, if there isn't superposition, my guess is the model just wants to align features with neurons, because in the model has features framework, the thing that we're expecting to happen is that the model wants to be able to reason about each feature independently without interference between the two. And the way that nonlinearity is like Relu and Jelly work is that each neuron is affected purely independently from the others, but that as you combine them, but that if there are multiple features in a single neuron, then those features will dramatically interfere with each other. And this is a pain. But yeah, this is all kind of just conceptual reasoning. I think that the toy models of superposition paper is like pretty good evidence that superposition might happen, but I want someone to go and check. Alright, there's a sudden extremely popular question on, can mechanistic interpretability be used for detecting deceptive alignment in models? So, 2 possible ways to interpret this. One way to interpret this is, can we use it right now to detect deceptive alignment? And I'm like, maybe? Probably not. We're not very good at it. We might be able to like get some insight into what's going on by just looking at the model and a bunch of example prompts and poking around to see if we can get any traction. But like, I don't know, seems hard, man. If I interpret this as, do I think that we could get to a point where we can use it to detect deceptive alignment? Yes, I feel pretty excited and optimistic about this. And I think that the world where mechanistic interpretability is extremely useful is worlds where it can help us get traction on detecting things like this. The key path would just be getting good at truth tracking and scalable ways to... getting good at truth tracking and scalable ways to detect which bits of a model are most relevant to producing specific outputs, and finding specific circuits within these, putting the model into a context where it could be being deceptive, and using these to try to get traction on what's going on and why. And hopefully, within a few years, the field will be at a much more sophisticated point where that story seems kind of boring and naive. And I think that there's a bunch of ways that you could raise the stakes and push back on this and be like, but if the model was truly deceptively aligned, then couldn't it just think its thoughts in a way that couldn't be mind-read? And I'm kind of skeptical of this, just because I think that models get good at being deceptive because they have a bunch of feedback on what they output, which outputs are good versus bad. But they have basically no feedback on their internal representations, how legible they are, and how much they can be interpreted. It's possible there are some high-level strategies, and I do expect that, say, GPT-4 will have read some of the circuits papers and known something about interpretability. And maybe there are strategies that a model could use to intentionally shape its own thoughts to be harder to interpret in a way that breaks these techniques. I think this seems significantly harder than any other form of breaking or ability to detect deception, but hard to rule out. Anyway, I think a lot of this depends on like how good we get, which, in my opinion, boils down to a bunch of pretty hard, unknown scientific questions. There is a fun question from Jesse Hoogland on what are your most contrarian ideas or disagreements with other interpretability researchers? So, let's see. Specific things coming to mind. Let's see. If I'm focusing on within mechanistic interpretability, I'm pretty bullish on just looking really hard at toy language models, and I think that we're just pretty confused about how to interpret even a one-layer model. This seems bad, and I think that solving this will teach us a bunch of things. And a lot of other people in the field seem excited about larger models, and on the flip side, I am inherently very skeptical of any toy model work that's trying to explicitly construct something, that is trying to model something useful about a language model, analogous to Anthropic's toy models of superposition work. And I'm broadly convinced that their toy models of superposition paper was good and actually tried to think about real models. They have a later one on toy models of like extenuative memorization, and I'm not actually very convinced that that one tracks something useful about real models. Another disagreement I have is I'm pretty bullish on the idea that models actually learn clean, legible internal structures that form circuits, and that we can actually find these and understand these. And I don't know, this is definitely a thing that strongly distinguishes mech-interp from the rest of interpretability, but even within mech-interp, I know, say, some researchers at Redwood who I think are pretty skeptical of that perspective. I also, let's see, I'm generally pretty skeptical of anything that boils down to explicitly put interpretability tools into the loss function, because I just think that having, that is, actually do gradient descent on something that involves an interpretability tool, because I think that having a tool that is good enough that we can robustly optimize against it just seems wildly unrealistic. Gradient descent is smarter than you are. And a lot of the things I'm excited about look more like enabling better alignment work and auditing models and noticing when they go wrong, rather than being just a fully fledged alignment solution where you can just train on don't beat on like our evilness metric and just win. Do I have other disagreements? I think one idea I've heard bandied around is this idea of enumerative safety. This idea that a way we can make models safe is by solving something like superposition, enumerating every feature represented in the model, and using this to understand, to just check, like, are the features we're concerned about, like deception or goals or situational awareness in there? And I think this would be pretty cool if it works, but it doesn't seem at all necessary to me to get this to work, to get useful things out of interpretability, and I think some people disagree with me on that. Entertainingly, I don't think my work on grokking was like that useful for alignment, and I know some interpretability researchers disagree with me on that, which is hilarious. I really wish I agreed with them because I feel way better about all that work. I mostly just don't think grokking is that great a model of things that happen in real networks, though I think there are some cool and useful lessons, and hopefully pretty good field building. Cool. I will end my list of contrarian ideas and disagreements there. Alright. I will probably wrap up, but yeah, this was fun. I will reiterate that if you found this talk interesting or inspiring, or just want to prove me wrong when I say that people can do mech interp research, you should go check out my Concrete Open Problem sequence, and that you should also go check out my Getting Started guide, and I'll put a link to the slides again in the Zoom chat. But yeah, thanks everyone for coming and for all the good questions. And thanks to Walter for the paper he linked in the chat. Did I hear a final question? Oh yeah, I'm also giving this talk in some other places, so feedback on it extremely well.
Thank you, Neil.